So welcome back to our next set of questions from the LEAP 2025 Geometry Practice Test. Let's go ahead and dive in. So it says that triangle ABC has vertices at A, B, and C in the coordinate plane, and the triangle will be, let's highlight a couple words, reflected over the x-axis and then rotated 180 degrees about the origin to form triangle A prime, B prime, C prime. What are the vertices of triangle A prime, B prime, C prime? While there are some functions that we learned on our transformations lesson, this one's actually a lot easier to do if you just think about what these transformations do instead of getting bogged down into memorizing the functions or even applying those functions. So, for example, let's just talk about these 3 points. So A is located at 1, 2, which we can say this is 1, so 2's up here. So let's just say that's A. And B is located at 4, 6, so somewhere over here and up a little higher, there's B. And C is located at 4, 2, so in line with B, but also in line with A. So in fact, I imagine it's going to make a right triangle, but we don't really need to know that. So there are some functions that you could use to solve this one. For example, a reflection across the x-axis. It's this function. Every point goes to, the x stays the same, and the y changes signs. And then for a rotation of 180 degrees about the origin, it's xy goes to negative x, negative y. But I'm going to show you that if you really just think about what these transformations are telling us, we don't actually have to do any of this kind of math here. So if it's reflected across the x-axis, which is this line right here, then it's going to end up in this quadrant right here, which is the fourth quadrant. If you didn't know it, this is the first quadrant, this is the second quadrant, this is the third quadrant, and this, of course, is the fourth. Well, after it's in the fourth quadrant, it tells us that it's going to be rotated 180 degrees about the origin. So starting from this point here, rotating 180 degrees around the origin, or half a circle, we're going to end up in, don't want to use purple again, let's use a different color. We're going to end up in the second quadrant. So let's just talk about the signs of coordinates in these 4 quadrants. So in the first quadrant, you have a positive x and a positive y. Notice the 3 coordinates that they gave us. All of the coordinates are positive. In the second quadrant, you're going to have a negative x and a positive y. That's because we went left on the x-axis and we're up on the y-axis. So it's negative then positive. In the third quadrant, you go left on the x and down on the y. So you're going to have a negative x and a negative y. And in the fourth quadrant, we went right on the x-axis, so a positive x, but went down on the y-axis, so a negative y. So we know that we are going to be looking for coordinates that have a negative x and a positive y. So look at A. We have a positive x and negative y. So none of those fit the bill. Look at B. We have a negative x and a negative y. That would have been, of course, the third quadrant. Now let's look at C. We have a negative x and a positive y. Well, that looks good. Negative x, positive y. Negative x, positive y. So that looks good for now. But let's just make sure that D is not a possible option. Well, D is a positive x and a positive y, positive x, positive y, and a positive x, positive y. So it's definitely not D. So without even using these functions, I know that the answer choice has to be C, simply because the signs match where I know the triangle will end up. And let's move on. Number 9 says Luke purchases a warehouse on a plot of land for his business. The figure represents a plan of the land showing the location of the warehouse and parking area. The coordinates represent points on a rectangular grid with units in feet. So part A says, what is the perimeter of the plot of land, and express your answer to the nearest tenth. So we probably need to highlight that, make sure we do that. nearest tenth of a foot in your answer in the box. So let's just go make sure which of these line segments refer to the plot of land. So it says Luke purchased a warehouse on a plot of land. So this warehouse here, which is this square, I believe, and this parking area have to be sitting on the plot of land. So we should assume that this right here is the plot of land, what I've just highlighted in blue. So they want us to find the perimeter of the plot of land. Well, perimeter is the total distance around a figure. So our task is now to find the total distance between each of these four vertices. And they even gave us the coordinates that represent those vertices. Now I'm going to show you a trick here. When dealing with distance, especially with coordinates, we utilize something called the distance formula, which is d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Well, you might be telling yourself, well, I'm going to have to use that formula 4 times to find the length of 4 sides of this shape. Not so. We only have to use the distance formula for diagonal lines. In fact, starting on this left-hand side, if you notice, it's a purely vertical line, and our x values don't change. So all we have to do is really find the distance between our y values. Well, how far is 60 from 0? Well, 60 units. And I believe they told us it was feet, so I'll go and mark it with a little apostrophe. Likewise, on a horizontal line, look at your coordinates. The y value, I'll do it in a different color, the y value doesn't change.
Teachers, you may release your students that are in.
So again, if you notice that the y coordinates here, the y values for these two coordinates, there's no change between them. So all we have to do is find the distance between our x values. And so the distance between 0 and 70 is, of course, 70. And we are dealing with feet, so I'm just going to put that little apostrophe there to represent feet. Now, the other segment that we're going to be able to do that with is this one here on the bottom. So our task is to find the distance between these two endpoints. And again, if you notice our y values, there is no change there. So all we have to do is find the distance between our two x values. So the distance between 0 and 50 is, of course, 50 feet. So we just found 3 sides pretty quickly just by looking at the coordinates. But this 4th side here, that is what we consider a diagonal, we are going to have to use the distance formula to find the distance, because if you notice, the x values are not the same and the y values are not the same. So we're going to go ahead and plug those values into the distance formula. It doesn't matter which coordinate you call your 1s or coordinate you call your 2s, as long as you're consistent. So we'll call 70 x1, so 60 y1, and 50 x2, and so 0 will be y2. So d will equal the square root of x2 minus x1, so 50 minus 70 squared, plus y2 minus y1, 0 minus 60 squared. We're going to start with order of operations, which is PEMDAS. And what the P in PEMDAS really means for parentheses, is there any work to be done inside the parentheses? So when we look within these two parentheses here, we can actually do that math. We can simplify 50, take away 70, and we actually get negative 20. And so we're going to do the same thing with this set of parentheses as well. And 0 take away 60 is a negative 60. So that's what the P in PEMDAS really means. Is there any work to be done inside the parentheses? Now we're going to move on to the E, which is exponents. So negative 20 squared doesn't mean negative 20 times 2. It means negative 20 times itself, which will give us a positive 400, because a negative times a negative is a positive. And then here, a negative 60 squared, again, is not negative 60 times 2, but a negative 60 times negative 60, which will actually give us 3,600 or 3,600. There is no multiplication involved or division, so we go and move into adding these two terms, and we get 400 plus 3,600, which is a nice 4,000. And now we have to take the square root of 4,000. So using my handy dandy calculator here, I'll admit that I am not too keen on the square root of 4,000. It is 63.2455, and it tells us that we're going to round to the nearest tenth. So I'm going to go and change this to D is approximately 63.2. So if you're looking at your calculator, you get 63.2455 and so on. Rounding to the nearest tenth, the 10th place, a 2 is in the 10th place, so we look to the number right behind the 10th place, and it tells us whether or not to round the 10th place up or keep it the same. And if it's 4 or below, we keep that number the same. So that's why I said that the distance between those 2 points is 63.2 feet. So now to find perimeter, which the definition of perimeter is total distance, we're going to simply add these 4 distances of these 4 sides. So 60 plus 70 plus 50 and plus our final measurement 63.2, and we get 243.2 feet. So I'm going to put that in our part A. And let's go and take a look at part B. So B says, what is the area in square feet of the plot of land that does not include the warehouse and the parking area? So we are trying to figure out the area, which is the total amount of space something takes up. So we're not really looking at perimeter at this point, although we will use some of the measurements we did earlier. We're figuring out the amount of space that the plot of land takes up that does not include the warehouse or the parking area. So what we're going to do is we are going to find the total area of the plot of land and then subtract the area that I'm highlighting in purple, the area that makes up the warehouse and the parking area. So I'm going to go and put it back a couple of our measurements. I remember this was 60 feet, this was 70 feet, 63.2 feet, and 50 feet. So there are multiple ways to do this at this point. It depends on what formulas you know or know how to use. I'm going to approach it the way that most of you will probably approach it on the test. So I'm going to take this point here and draw a vertical line to make this rectangle. And then once I find the area of this rectangle, then I'll find the area of this triangle and add it to it. So if this is 50 on the x, this will be 50 on the x as well. And it will be the same y value, which will be 60. So that point is 50, 60. And that's going to be important here in just a second. So the total area, let's find the area of this rectangle here. So we're looking at now the distance, instead of 70 feet, we're looking at from 0 to 50. So we're actually only going to use 50 feet here. So the area of this rectangle, and I'm going to draw it kind of smaller here, just kind of clean it up. The area of this rectangle is simply length times width. So we're going to take 60 feet, which we'll call our length, and 50 feet, our width, and simply multiply those together. And 60 times 50, I believe, is 3,000. So that is 3,000 square feet, or feet squared. So that's the area of this rectangle as of now. We still need to find the area of this triangle. So the area of this triangle, we need 1/2 base times height. That's because if you think about it, a triangle is half of a rectangle. So your base and height, and I probably said that pretty quickly, but area of a triangle is 1/2 base times height. Your base and height are the two sides that make the right angle. So that's why I drew this vertical line here. So these two lines that I'm highlighting in blue are going to be our base and height. So we need the measurements of those. We already know that because this is a rectangle, this is also going to be 60 right here. So 60 feet, we'll call that our height. And then our base from 50 to 70 will be 20 feet. So we're going to do the area of the triangle is 1/2 of 60 times 20. Well, quick math, half of 60 is 30, and 30 times 20, I believe, is 600. So the area of this little triangle here is going to be 600 square feet. So to find the total area of the plot of land, we just simply need to add these two areas together. So 3,000 square feet and 600 square feet will give us a total of 3,600 square feet. But remember, we still need to subtract the area of the warehouse and the parking area. Now, I'll be honest with you, if you understand the area formula of a trapezoid, that would actually have been the easiest formula you could have used to find the area of the plot of land. But the way I'm looking at it here is I'm trying to show y'all what more than likely students are going to do. So if you understand the area of a trapezoid formula, go for it. You can just do that math a lot quicker, honestly. So now let's find the area of the warehouse. So the area of the warehouse, I'll kind of draw that and the little parking area. So the area of the warehouse is just, it's a rectangle, I believe, or it could be even a square potentially, but it's just length times width. So we only need two distances here. So notice that the y values for these 2 points are the same. So we just really need to find the distance between our x's. So the distance between 4 and 39 is 35. So we'll call that our length, if you will. And then to find our width, notice that the x values are the same between these two coordinates. So all we really have to do is find the distance between these two y values. So between 50 and 20 is 30 feet. So now we're going to take 30 feet and multiply it by 35, because the area of a rectangle is just length times width, and we get 1,050 square feet, or feet squared. Well, now we have to find the area of the parking. So I'm going to do it the same way. I'm going to divide it into a rectangle and a triangle here. We can't forget that little triangle. So we already know that this length is 35. We just need to find the height here. So I believe the height of this point is 20, and the height of this point is 0. So the height of the parking area would be 20 feet. So to find this portion right here, we just need to multiply 20 times 35, the length times the width, if you will. And we get 700 square feet. Last but not least, we need to find the area of our little triangle. And really the trapezoid formula here would be best as well, because the parking area is a trapezoid. So if you do understand how to use that formula, go for it. So we need these two measurements here for a triangle, because the base and height from the formula of a triangle is those two sides that make a right angle. So we know the height of this triangle is 20, because it's the same as over here on the rectangle. And then from this point, we need to go from 39 to 50, which will be 11. So we're going to do 1/2. I'll put that work here. 1/2 times 20 times 11, which is 1/2 base times height of this tiny little triangle. Half of 20 is 10, and 10 times 11 is 110. So the area of this little triangle here is 110 feet squared. So let's combine all of these areas that we just found, 1,050 plus 700 plus 110. And this total area that the warehouse and the parking area take up is 1,860 square feet, or feet squared. So they asked us to find the area of the plot of land that does not include the warehouse or the parking area. So now what we're going to do, if 3,600 square feet is the total of the plot of land, and this is the area from the warehouse and the parking area, we're going to simply subtract these two. So 3,600 Forgot the 6 for just a moment, and 1860. And we get 1,740 square feet, or feet squared. So let's go and put that into our part B, 1,740. Part C says Luke is planning to put a fence along 2 interior sides of the parking area. The sides are represented in the plan by the legs of there's that word that I've been mentioning a couple times, the trapezoid. What is the total length of the fence included? So Luke is planning to put a fence along just 2 sides of the parking area, and it's the legs of the trapezoid. And so we are asked to find the total length of the fence needed, and it's going to be nearest tenth of a foot. So let's take a look at that. So now we definitely have to address what it looks like for the parking area to be a trapezoid. So in a trapezoid, these 2 parallel sides have to be what's called the bases. So these 2 sides that I highlighted in orange are the bases. Therefore, these other 2 sides are called the legs. So to find the distance of the fence along those sides, we need to find the distance of these 2 line segments. Now, this one's going to be a little bit easier for us because it's a vertical line. If we notice that our x-coordinate is the same value, but our y-coordinate is different, so all we have to do is, again, find the distance between the 20 and 0, which is 20. So we know one distance of a line segment is going to be 20 feet. But this one, if you recall, just like we did at the part A, it's a diagonal line. So we have to use the distance formula to find the distance between these 2 coordinates here. So that's what we're going to do. D is equal to the square root of, let's go and label, I'll call this my x1 and y1, and this will be my x2 and y2. So D will equal the square root of x2 minus x1, which will be 50 minus 39, squared, plus y2 minus y1, which will be 0 minus 20, squared. Remember, PEMDAS tells us to do parentheses first. So we're going to actually subtract 50 minus 39, which will give us 11, 11 squared, and 0 take away 20, which is negative 20, and we're going to square that. So 11 squared is 121, and a negative 20 squared, which again is negative 20 times negative 20, which would be a positive 400. So D will equal the square root of 121 plus 400 should be the square root of 521. Now, many of you learned how to simplify square roots, but if you notice the directions ask us to round it to the nearest tenth. So if they tell you to round to the nearest tenth of a foot, you don't need to actually simplify this square root. You can simply take the square root of 521 in the calculator to find its decimal approximation. So the square root of 521, in my calculator, I get 22.8254 and so on. And so just a reminder that the 8 is in the tenths place. So we look to the number right behind it, and that 2 tells that 8 to stay where it is. So the distance of this diagonal line of the parking area is going to be approximately 22.8 feet. So to find our final answer, we're just going to combine the 20 feet from this left side and the 22.8 feet from this right side, and we should get a total, just to show you, you should get a total of 42.8 feet. So that's what we're going to go in and put in that box down there. Part D, which I'm hoping is the last one here, and it is. It says, in the future, Luke has plans to construct a circular storage bin. Way to go, Luke. Centered at coordinates 50, 40 on the plan. which of the listed measurements could be the diameter of a bin that will fit on the plot of land and be at least 2 feet away from the warehouse? It says select all that apply. So because it says at least 2 feet away, that's why there's multiple options here, and that's why they say select all that apply. So that's what we have to figure out. So in the future, Luke has plans to construct a circular storage bin at coordinates 50, 40, which of the listed measurements could be the diameter. So real quick on a circle, you all know what a circle looks like, although that's a pretty terrible one. A diameter is a chord that passes through the center of the circle. So this is the center of the circle. The diameter is the chord that passes through it. And the diameter of a circle, because a circle is round, and what makes it round is the diameter all the way around this circle is the same length. So we really have to figure out in many different directions which of these diameter measurements will work. So let's take a look at our diagram. So they tell us that he plans on putting a circular bin at 50, 40. So 50 is right here in this line, and 40, well, if this is 50 up here, 40 is going to end up somewhere probably in this region. So we need to figure out what could be the diameter of the circular bin so that it's at least 2 feet away from the warehouse. So let's first think about how far the center of this circular bin will be from the warehouse. So if this was 50 and this was 39, this is a total of 11 feet from the warehouse. Now, we need to keep in mind that that's only the radius of the circle, or the largest circle we could even put inside of here. So the total diameter would be 2 radiuses together, which would be 22 feet. Remember, it said that it has to be at least 2 feet away from the warehouse. So 2 feet on this side over here. So the greatest possible, if 11 is the max and it would touch the warehouse, then 2 feet less of that has to be 9 feet. So we're talking about a radius of our circular bin of just being 9 feet, which again, we have to keep in mind that we're not talking about the radius, we're talking about the diameter. So it'd actually be 2 9 feet sections. And so for a total, the max we could do would be a total of 18 feet for our diameter, because we have to be 2 feet away from the warehouse on that left-hand side there. So we can select 18 or fewer. So let's take a look at our options down here. Let's just read the question again. Which of the listed measurements could be the diameter of a bin that will fit on a plot of land and be at least 2 feet away from the warehouse? So we're talking about 18 or less. So we could do choice C, B, or A. So again, we can't use 22 because it would touch the warehouse, and obviously couldn't do 25 because it would be overlapping the warehouse. So that's how we figured out part D. And I'm hoping that's all the parts of this one problem. So now let's move on to question 10. So the right triangle in the coordinate plane is rotated 270 degrees clockwise about the point 2, 1, and then reflected across the y-axis to form triangle A prime, B prime, C prime. It says graph the appropriate orientation. That just really means the direction of it. You know, like a sheet of paper, this is what we call portrait orientation, or if you turn it on its side, landscape. So just really kind of the direction of it. And they really emphasize that with the triangle. There's kind of this overall direction of it pointing up, if you will. So it says graph the appropriate orientation for triangle A prime, B prime, C prime on the coordinate plane. So let's see how this graphing option works. So they tell us over here, we're going to click to select, and then we'll actually graph our triangle. So we need to figure out, where are A prime, B prime, and C prime going to be? So for starters, we are tasked to rotate 270 degrees clockwise about the point 2, 1. Well, if you notice that our pre-image, this is what it's called before the any transformation, is that our center of rotation is actually on our pre-image, 2, 1. So if you recall from our lesson from rotations, is that the center of rotation does not move. So in this 270 degree clockwise rotation, point A is not going to move at all. It's going to stay in its same place. So only C and B are going to move 270 degrees clockwise because the center of rotation does not move. So like the other transformation problem that we were using, I wanted to just get you to really understand what these transformations are asking us instead of getting really focused on all the functions. But if you want to know the function for 270 degree clockwise, it's this. XY goes to, it's also the same as 90 degree counterclockwise. I should go and point that out. That 270 clockwise is the same as 90 degrees counterclockwise. So every point will go to swap y and x and change the sign of your y. So that's the function for those that really want to rely on the function to perform this. Now, when it's a rotation around a point other than the origin, you can't just simply use that function. You have to do some pretty lengthy math involved. So that's why I'm looking at it a little bit differently. And also, if you want to reflect across the y-axis, the function for that is xy goes to x stays the same. Nope. A reflection across the y-axis, the x is going to change signs and y will stay the same. But I'm going to look at it a little bit differently. So that's why I mentioned that. But feel free to use those functions if you want to. So if we're rotating 270 clockwise or 90 counterclockwise and point A is not going to move, let's think about that. So here we have line segment AC, and I know that this line segment along with point C is going to rotate 90 degrees counterclockwise. So in other words, AC is going to go from being horizontal to vertical, right? Well, if AC is 3 units wide, when it rotates, it still has to be 3 units wide. So I know that C is going to end up right there because a rotation is a rigid transformation. So it's not going to change the length of any of our segments. So if you notice, there's a right angle here. So I know C is going to end up right there. Well, then think about how far C is from B in the pre-image. C is 1, 2, 3, 4, 5 units from B. So B has to remain 5 units from C. So 1, 2, 3, 4, 5. So B is going to end up right here. So if you kind of picture it, the triangle was pointing up and now it's pointing left, if you will. And that is a 90 degree counterclockwise rotation. So that part we actually did correctly without using the function. And then it tells us that we're going to reflect across the y-axis. Well, if you recall from our lesson on reflections, however far a point is from the line of reflection, that's how far it has to travel on the other side of the line of reflection. So we're reflecting across the y-axis, which I'll highlight in purple here. So B, we'll start with A. Why not? So A is 2 units from the y-axis, so it's going to end up 2 units on the other side of the y-axis. So A prime is ultimately going to end up there. Likewise with C, C being 2 units from the y-axis, has to travel 2 units across the y-axis. So here we have A prime, C prime, and we'll officially graph it with this tool over here in just a moment. Our last point, B, is 1, 2, 3 units from the y-axis. So when it reflects, it has to move 1, 2, 3 over the y-axis. So B prime will be here. So my final image, and I should probably highlight that in a color I haven't used, so we'll use yellow. Our final image is going to end up here. So I'm going to write those coordinates off to the side just so I make sure I don't mess them up when graphing. So A prime is going to be at -2, +1. B prime is going to be located at 3, positive 4. And C prime is going to be located at negative 2, positive 4. So now I'm going to clean all this up so I can actually graph it using the tool they provided. So I believe we need to click to select. And then I'm going to go and plot my points. I'll start with A prime, which is at negative 2, 1. And then if you notice, it went ahead and graphed the entire triangle, but obviously we need to move these points. So we're going to go ahead and grab C prime. I just clicked on it, and I'm going to move it to negative 2, 4. And then I'm going to click on B prime, and I'm going to move it to 3, 4. So again, we rotated 90 degrees counterclockwise and then reflected it across the y-axis. So that is number 10. Let's move on to number 11. So number 11 says each of the two-dimensional figures shown will be rotated 360 degrees about the respective line. So we're rotating a full circle, if you will, creating a three-dimensional figure. And it says drag the appropriate two-dimensional figure to identify the correct representation of the resulting three-dimensional figure. So for example, on this first one, we're going to take a rectangle and rotate it around this line to create a three-dimensional shape. What we're doing here is we're using what's called nets of two-dimensional figures to create three-dimensional. So all these are rotating in a circular fashion. So each of these is going to have some form of a circle. If you notice, this is, in fact, it's a ring. So if you think about it, it's really just a bunch of circles over and over again in a circular form. This one here is a circle that somehow gets smaller, 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 smaller. This one is a circle that stays the same width the whole time. We call this a cylinder. This was a cone. And then we have here a circle that gets smaller as it goes up and somehow smaller as it goes down. And we call that a sphere. So I'll clean all that up. So for this first one, we're dealing with a two-dimensional figure that is a triangle and then somehow produces a three-dimensional figure in a circular motion, which hopefully you can tell it's going to be this one that involves these two measurements are the same width. That is based on this being a rectangle. So I'm going to go and grab that one and drop it above like I'm supposed to. Now let's look at the next one. So the one that has a triangular shape, most people probably can figure this one out. The reason this circle got smaller and smaller and smaller and smaller is because on this triangle, of course, the distance between this line and these other points gets smaller and smaller and smaller. So hopefully nothing too complicated on the circular cone. Almost called it a pyramid. How terrible. Let's make sure that goes there. And then often what I see, the struggle that most students have is deciding between these two. So let's talk about the main differences between these two. Here we have a circle, first of all, a whole circle that is not on this line that it's rotating around. So as it overlaps itself, creating a three-dimensional figure, there has to be space between where it is and where it was at the beginning and end of the rotation. However, on this one, if you notice, it's only a half circle and part of it is on the line. So there won't be any space between any parts of this circle as they overlap. So with that in mind, because this one has space between the line it's rotating around, that's what caused this hole in this ring shape over here. So we're going to drag this one to the ring, if you will, call it a ring. I'm sure there's a better geometric name for that. And we'll drag this one to the sphere at the end. Okay, moving on to question 12. So the figure shows parallelogram PQRS on a coordinate plane diagonals SQ and PR intersect at point T. Part A says find the coordinates of point Q in terms of A, B, and C, and enter your answer in the box. So if you notice, at each of these points, P, Q, R, and S, they don't actually give us the number values that represent the coordinate on the coordinate plane. They tell us that P is located at 2B and 2C, and R is located at 2A and 0, and S is located at 0, 0. So they want us to know the coordinates of Q in terms of A, B, or C. So a couple properties of the parallelogram are opposite sides are parallel. That's actually its definition. So these two sides are parallel, so they're going to have the same slope. And these two sides are parallel, so they're also going to have the same slope. And I'm mentioning all this now because it might help us, because I imagine there's a part B. Not only are opposite sides parallel, but opposite sides are congruent, which is really going to help us determine the coordinate of Q. So a parallelogram, if you think about it, because it has opposite sides and opposite sides are congruent and parallel, it's a lot like a rectangle. A rectangle has opposite sides parallel and opposite sides congruent. The only difference is there's no 90-degree angles. So what we're going to do is we're going to think about this parallelogram in terms of if it was a rectangle. So I've just drawn a rectangle here, because if you notice now, if I look at it as a rectangle, this coordinate here is one of the corners or vertices of our rectangle. So if I can find the vertices of the corner of that rectangle, maybe it won't be as daunting. So let's find out the distance from here on the y-axis to this point. So we know if we're dealing with a horizontal line that our y value is not going to change. So this point would be 0 to C. And so the distance between these 2 points would just be the change in our x value, which is 0 to 2b, and 2b minus 0 is simply 2b. So the distance here on a rectangle is 2b. Well, if you didn't guess it, this triangle that I added to our diagram is the same as this triangle over here. So if the length of this segment is 2b, the length of this segment also has to be 2b, which is going to help us, because if R is located at 2a and we're trying to figure out this coordinate here, and the length is 2b, we can simply add our x value 2a to 2b, knowing that the y value is not going to change. So the coordinate of this point we'll call z, because it's not being used, will be 2a plus 2b, 0, because we're still horizontal to this original point, so it's going to have the same y value. Now what we have to do is find the, because we drew a vertical line here, so this x value for this coordinate is going to be the same x value for this coordinate. So Q will definitely have an x value that is 2a plus 2b. Then we need to figure out its y value. Well, because it's parallel to this side here, it's going to have the same y values, all these other y values on this line. It's a straight line. So the y value here was 2c, the y value here is 2c, therefore the y value here will be 2c. So the coordinate for point Q in terms of A, B, and C are 2a plus 2b, comma, 2c. So I'm going to go and show you how to put that in the box here. So parentheses, 2a, I don't think they have any special math functions on this one. 2a plus 2b, comma, 2c, and close parentheses. Let's take a look at part B. It says since PQRS is a parallelogram, SQ and PR bisect each other. So what SQ and PR, let's go look at our diagram. SQ and PR, are the diagonals of our parallelogram. So yes, they do bisect or intersect at point T. Let's just make sure before I get ahead of myself. And it says that they also bisect each other. So just to show you what that means real quick. If they bisect each other, that means PR, the way I look at it is PR is acting as a knife to cut SQ into two congruent parts. That's what bisect means. So ST is going to be congruent to TQ. So I'm going to go and write that. It might help us out. And likewise, SQ is acting like a knife that's cutting PR into two congruent segments. So PT and TR will be congruent. So PT and TR will be congruent as well. So that might help us. It might not. Just letting my thoughts kind of flow on this problem. So let's go back and look at the question. So it says use the coordinates to verify that SQ and PR bisect each other. So we can't just say they bisect each other because we know that they do. We need to show that they bisect each other. Well, what I've shown over here is that ST and TQ are congruent, which means they're the same measure. So if I can show that the length of ST is equal to the length of TQ, and likewise show that PT is equal to the length of TR, I can prove that they do in fact bisect each other. So I'm going to go and write the coordinates for Q again. 2a plus 2b, comma 2c. And so if we're trying to prove that segments are equal, we need to show that the distance between those 2 points are the same. So we need to show that the distance from S to T is the same as from Q to T. So we learned about a special point in geometry, a point that bisects a segment into two congruent segments. So, and it's called the midpoint. So if I can show that T is the midpoint of SQ, then PR bisected SQ. So I need to show that T, for starters, is the midpoint or the halfway point of SQ. So midpoint is, the midpoint formula is x1 plus x2 over 2, comma y1 plus y2 over 2. Now, this is not the only way to do this, but this is definitely the way I'm approaching it. So x1 plus x2 tells us to add our x's, and y1 plus y2 tells us to add our y's. So we'll add 0 and 2a plus 2b for our x's. And I know that looks crazy, but just bear with me. Over 2. And our y's, 0 and 2c over 2. So 0 or 2a plus 2b plus nothing is still going to be 2a plus 2b over 2. And 2c plus nothing is still going to be 2c over 2. So I'm going to show you something pretty mathematically cool here. There's really the way to approach this is that both of these terms have a common factor of 2. So I can actually divide 2a and 2b by that common factor. And I'm going to rewrite it as 2 times a plus b. Because if you think about it, if I multiply 2 times a, I get 2a, and 2 times b, I get 2b. I'm back where I started. So I factored that common factor out. Well, on this right-hand side, it might be a little bit more obvious to see that 2c divided by 2, the 2's can actually divide and become the number 1, or we call that cancel. So all that we're left with is c, or 1c. Well, in the same fashion, and this is why algebra is so cool, is that the 2's here can also divide by each other in the same way that they did on this y coordinate, and 2 divided by 2 becomes 1, so all we're left with is a plus b. So, little roundabout here, the midpoint of, or the coordinate for t, or the midpoint of SQ is a plus b comma c. So we just showed that the midpoint of SQ is a plus b comma c. Now you might be asking yourself, well, how does that help us show that, PR bisected, or excuse me, SQ bisected PR? Well, if we can find the midpoint of these 2 points of PR, and it's the same location, the same coordinate, then that proves that SQ also bisected PR at its midpoint T. So we're going to also show that the midpoint of PR is this coordinate here, a plus b comma c. So I'm going to erase some things so I can have some room. So I'll do that here. So we already know what the midpoint formula is. So I'm going to now add my x's to a and to b and put that over 2, and 0 plus 2c. And some of you hopefully already noticing that we're ending up in the same spot that we did right here. So of course we'll factor out that 2 again. And simplify to get a plus b comma c. So I'm not going to type this all out here, but what we did was we showed using the midpoint formula that the midpoint of both SQ and PR is a plus b comma c. Well, a midpoint is a point that bisects a segment into 2 congruent segments. So by showing that point is the midpoint for both segments, we have just proven that each segment bisects the other. So I'm not going to go through the lengthy process of typing that out. You, of course, are more than welcome to do that. And I suggest you do it, especially on the actual test. Let me make sure there's not a part C here. Doesn't appear to be, so we'll go and move on. Of course, I'm gonna go and skip because I didn't type anything to that part. Some of you will recognize this problem because I've actually had it on a test before, so we'll work through it. So part A says a seesaw with the construction shown as being built at a playground. The seating board will be 8 feet long, and the board will make an angle of 25 degrees when it touches the ground, as we see here. It says, create and use a model to find the height of the central support. Show your work or explain your answer. Round your final answer to the nearest 10th of a foot. Enter your model, your answer, and your work or explanations in the box provided. So our task is to find the height of the central support right here. And the first thing I want to just really emphasize or show you is that RT is a side of a triangle, and not just any triangle, but a right triangle. So anytime you see a right triangle in your test, you need to initially think Pythagorean theorem, that might be a possibility, or our trig functions, sine, cosine, or tangent. And I'll tell you for sure that we're going to have to use sine, cosine, or tangent. So we're going to use right triangle trig here using sine, cosine, and tangent. So sine, by its definition, sine of an angle is the opposite side length over the hypotenuse. Cosine of an angle is the ratio of the adjacent side length over the length of the hypotenuse. And tangent is the tangent of an angle is the ratio of the opposite side length over the adjacent side length of that angle. So when deciding whether or not to use sine, cosine, or tangent, you have to figure out, well, what information do you actually have? So we were definitely given that angle S is 25 degrees. Now, truth be told, we could also find angle R because we know angle T and angle S, we can find angle R because all three angles of any triangle have to equal 180 degrees. But it's a little unnecessary because we just need one angle measure for starter. We are trying to find RT, which in relation to angle S, what we're given, RT is considered the opposite side of this angle. So we are more than likely going to use sine or tangent because they involve the term opposite. So we're going to kind of push cosine to the side for now. Well, if you notice in a ratio or in these ratios, we need an opposite side length and a hypotenuse side length. Or for tangent, an opposite side length and an adjacent. So the next thing we're going to use to determine which trig function is we're going to figure out, do we have the hypotenuse or do we have the adjacent side of angle S? Well, they told us, I don't know what that was, they told us that the length of the seesaw was 8 feet. So we are supposed to assume that halfway at point R, from R to S, is only 4 feet. So we actually have the length of this side of this right triangle. So we have to ask ourselves, is RS considered an adjacent side to angle S, or is it considered the hypotenuse? Well, it seems like it would be considered adjacent to angle S, but RS is the hypotenuse of this right triangle because it is opposite of the right angle. That's how we describe the hypotenuse. It's opposite of the right angle. So, in fact, we have our angle measured 25 degrees. We're looking for the opposite side length of that angle, and we're given the hypotenuse. So we are going to be using the sine ratio here. So the sine of, and this symbol here stands for theta, which represents an angle measure. That's all that is. So the sine of 25 degrees is equal to, and this is what I would be typing in, all these things that I'm saying, we should go through the process of explaining it and typing it in. I'm just trying to demonstrate how to solve the problem. So sine of 25 is equal to the opposite side length, which is RT, over the hypotenuse, which is RS, or you can go and replace RS with 4. And I'll go and show that it's 4 feet. So to solve for RT, or at least the way I approach it, by the way, sine of 25 degrees is a number. If you put sine of 25 degrees in your calculator, you do in fact get a number. And I'll show you what that number is using this desktop calculator. So first thing I need to do is make sure I'm in degree mode. That's not really important at this point, but you definitely need to be in degree mode because we're dealing with degrees. We've explored a little bit of what radians are, but for the sake of this, I just need to make sure I was in degree mode. So the first thing I want to show you is that sine of 25 is a number. It's a decimal. It's representing a ratio of any right triangle in the world. When you compare the opposite side to the hypotenuse, if it involves a 25-degree angle in the right triangle, you're always going to get this decimal, 0.4226. So please understand that sine of 25 degrees is a number. That's what I'm trying to establish there. So if that's the case, I'm going to put sine of 25 degrees over 1 so that this is now a fraction equaling a fraction, aka a proportion. And to solve a proportion, we're going to cross multiply. So I'll multiply RT times 1 and get RT, and then I'll multiply 4 times the sine of 25. So notice right here, I can find the length of RT simply by multiplying 4 times the sine of 25. So that's what I'm going to put in my calculator. 4 times the sine of 25. And I get 1.69. They actually tell us to round our final answer to the nearest 10. So in this case, 6 is in the tens place. So the 9 right behind it tells that 6 to round up. So the length of RT is approximately 1.7 feet. So just for the sake of this problem, again, you should be explaining all this and typing this in. Just so it doesn't want me to, or ask me to skip, I'm just going to type in 1.7 feet. Please know that that is not enough on these constructive response questions. Part B then says the seesaw moves and the angle created by the left side of the seating board and the central support is now 80 degrees. So they now tell us that angle R is 80 degrees. It says create it and use a model to find the distance from point Q, which is right here, to the ground. So we are now trying to find the distance from point Q to the ground. You always have to assume when we're talking this distance here that they mean a perpendicular distance to the ground, so a right angle. So it says show your work or explain your answer. So our task is to find Q. Now this is one way I'm going to approach it. There's other ways, and if you search for this on the internet, you'll see other ways to do this. But we already know that the length from RT is 1.7 feet. So what I'm going to do is create a perpendicular segment from point Q that is perpendicular to RT. In other words, making this right triangle here. Reason being is I already know that the distance from RT, I don't know what that line is, the distance from RT is 1.7. So if I can find this distance here, and I'll highlight it in a slightly better color, if I can find this distance, and we'll call this point M, so if I can find that distance from R to M, I can subtract it from 1.7, the height of the central support, and I'll find this distance from Q to the ground, or from M to T. So that's how I'm going to approach it. So they tell us that we have the measure of angle R, which is 80 degrees. And we definitely know that the length from Q to R is 4 feet. It's still the same seesaw. And so I need to find what I'm now going to highlight in pink, the distance from R to M. So we're going to decide a trig function once again based on what we're given. So in relation to angle R, which is 80 degrees, we are supposed to find the adjacent side length. So I definitely need the a trig ratio that involves adjacent, which when I think about the sine function, which is opposite over hypotenuse, we are not going to do the sine function here. But we could still use tangent or cosine. So let's figure out what else we have. So not only are we looking for the adjacent side, but we are given, again, the hypotenuse. Our seating board is the hypotenuse of our right triangle. So which trig function uses adjacent and hypotenuse? Well, none other than cosine. The cosine of an angle is the ratio of the adjacent side length to the hypotenuse of the right triangle. So that's the trig function I'm going to use. So remember, theta represents our angle measure. So cosine of 80 degrees is equal to the adjacent side length, which I'm calling RM, over the hypotenuse, which they told us is 4 feet. Again, just like sine of 25 was a number, I'm going to show you that cosine of 80 is also a number. It's a decimal, 0.1736, and so on. So with that in mind, I'm going to go and put cosine of 80 over 1 and solve this proportion by cross multiplication. So I'll multiply Rm times 1 and get Rm equal to 4 times the cosine of 80. So if we just multiply 4 times the cosine of 80, we'll find the distance from R to M. So keep in mind we aren't exactly on our final part of the question. We still have a little more work to do. So 4 times the cosine of 80 is 0.694, which if we're rounding to the 10th, we can go and round Rm to 0.7. Because the 9 tells us 6 to round up. So the distance from R to M is 0.7 feet, and the total distance from R to T is 1.7. So what will be the distance from Q to the ground, or from M to T, rather? Well, 1.7 take away 0.7. So the distance from point Q to the ground, 1.7 take away 0.7, will be 1 foot. So I'm going to go and type that in. Of course, please type in a better explanation than that, or not just your answer, because they do check these constructive responses. Number 14 says use the triangle to answer the question. In right triangle ABC, the measure of angle B is not equal to the measure of angle C. That's pretty important here. So it says let sine of B equal some number, so R, and cosine of B equals some other number, S. They want to know what the sine of C minus the cosine of C is. The sine of C minus the cosine of C. So by definition of those trig ratios, sine of an angle is equal to the opposite side over the hypotenuse. But it all depends on which angle you're looking at. For example, if we're looking at angle C, the opposite side of C is AB. And of course, BC will be the hypotenuse, which means that AC is considered the adjacent side to C. Well, what happens when we're no longer looking at angle C, but we're looking at angle B, and we try to use these two terms, opposite and adjacent? Well, in fact, opposite of angle B is AC, which was the adjacent side to angle C. Therefore, BA is the adjacent side to angle B, which was the opposite of angle C. So what are we getting at here? Well, the sine of one angle, we'll call it A, or let's use a different letter. The sine of one angle, we'll call it X, is actually equal to the cosine of its complementary angle. So it'd be two complementary angles are those that add to equal 90 degrees. So the sine of X is equal to the cosine of its complementary angle. So in this case, the sine of B is actually equal to the cosine of C. And the opposite, the sine of C is equal to the cosine of B. Because of the very fact that when describing the opposite and adjacent side, they switch based on which angle we're looking at. So sine and cosine of complementary angles are actually equal. So if they tell us that the sine of B is R and sine of B is also equal to cosine of C, then in this problem, I can replace cosine of C with R. Likewise, if the sine of C is equal to cosine of B and they tell us that the cosine of B is S, then I can replace sine of C with S. So simply put, and I say simply put, it's just an understanding of that sine and cosine of complementary angles are equal. And so that's why they tell us that measure of angle B and measure of angle C are not equal. That would actually create a slightly different problem. So what does sine of C minus cosine of C equal? Well, S minus R. So that is item 14. That's going to end this next set of questions. Hopefully that's helping. Thank you for watching.